Good morning, ladies and gentlemen. My name is Papken Hovsepian. I'm head of the Thin Films Research Center at Sheffield Hallam University, and I'm very grateful for the organizing committee to invite me on this event. I'm a former Bulgarian graduate, so my career in PVD started in this country, and I'm very happy to come back and share what we have done further in foreign countries. Now it is about titanium aluminum carbonitride, vanadium carbonitride thin films, which are dedicated to machine aluminum and titanium alloys. Now these alloys are widely spread in industry, especially in automotive and aerospace, but machining of these soft alloys is extremely difficult because they tend to react with the cutting tool and mask the cutting edge by forming transfer layers. So the problems is the formation of this build-up edge. You get high cutting forces, you have very high surface roughness, and the tool lifetime is very short. So the solution is to find materials which are inert, which prevent these metallurgical reactions on the surface with low friction coefficient and high wear resistance. It's very easy to formulate the demands against your coating, but it's very difficult to achieve it. Now we are using a specialized equipment for magnetron sputtering. This is the machine, the overall look of the machine. It's a 4 magnetron system. This is a cross-section schematic of the system. Inside we have a turntable where we can mount the workpieces, cutting tools. We have 2 different materials coming from these plasma sources, one different material coming from this plasma sources and another material coming from this plasma source. And by sequential exposure of the surface, we can deposit a very thin nanoscale multilayers, and you will see how it looks like in the next few slides. So this is the overall structure of our coating. So this is the substrate, followed by transition layer, and then this is the main layer. This is a low MAC TM, so you cannot see the multilayers. But if you go to high resolution TM, you can clearly see these stripes here, and these are basically titanium aluminum nitride, vanadium nitride. This coating is free of carbon. But if you add carbon to this coating, titanium aluminum nitride, vanadium nitride, what you see that you get a white phase which is segregated right at the interfaces. And you can see that the thickness of each individual layer is approximately 1.1 nanometers. So delta is the thickness of 2 double layers. It's carbon because using different imaging SEM techniques, you can see that it is decorated in white, in bright field imaging, and in Z contrast it is black, so this is a light element. And we have lots of analysis which we have done across these layers, and we know that it is carbon. Now when cutting test is performed, what we are investigating, we are cutting a piece of metal and we are measuring the flank wear of the cutting tool. So when the flank wear reaches this point, approximately 0.25 microns, then we declare that this is the end of the lifetime. So this coating, for example, has only survived some 300 passes. This coating, which is DLC, diamond-like carbon coating, has survived 2,000, but with our new coating we can go up to 8,000 passes and machine aluminum alloy, which is high-strength aerospace grade. We have achieved similar good performance in machining titanium. So you can see these are orthopedic implants machined with the new coating, and we can see that we can go to at least 2 or 3 times more components to be produced with this coating compared to uncoated. Now, the main reason for this good performance is the accumulation of the carbon at the interfaces of the individual layers. I said that these individual layers are nitrides, titanium nitride or vanadium nitride. When you don't have carbon, the bonding between these layers is extremely strong, so you have a build-up edge formation, and when this build-up is removed due to the cutting forces, a big chunk of your coating will disappear, so therefore the lifetime is very short. But if you segregate carbon as we have done it, then you have a very low shear strength interface. So when the build-up edge starts forming, the tangential forces will delaminate this interface, and you expose permanently fresh surfaces of this coating, and therefore you get this very good performance. So these are my conclusions. Instead of reading them, I would like to tell you that with this coating at the moment, we are drilling holes in the wings of the planes produced by Airbus. So with uncoated tool, they can drill only 4 holes in the metal matrix composites from which the wings of the A380 are made, and these are wing structures along the size of this room, probably, so you can imagine how many holes you need to drill. And with the new coating, we can go up to 145 drills. And the drill gun, if you go to Airbus, is 25 kilos. So every time you drill a hole, you have to Arnold Schwarzenegger to do it all day, you know? So these are the applications which we are trying to address with this type of coatings. Thank you for your attention.